The year is 1944. The Second World War has entered its final phase, and the outcome in Europe is no longer seriously in doubt. But the air war over Germany is still grinding through aircraft and crews at a rate that will not slow until the very end. Downed German aircraft were crated up and shipped back to testing facilities in Britain and the United States, where engineers stripped them to the frame to find out what the enemy knew that they did not. What they found was uncomfortable. The wing spars and the load-bearing fittings inside those aircraft, the parts that carry every flight load the airframe sees, had been squeezed out of solid aluminum in single pieces under thousands of tons of pressure. No factory in America could do that. Within 10 years, the United States would own the two largest forging presses on Earth. Within 60, it would be buying them from Germany again. You are watching Trade Archive. If the machines that built the industrial century are the kind of thing you want more of, take a second to like this video and subscribe. Then we start with a treaty that nobody thought had anything to do with aircraft. But first, let's understand what a forging actually is. When you cut a part out of a solid block of metal on a milling machine, you are removing material. The grain of that metal, the internal fiber structure left over from when the ingot solidified, runs straight through the block in whatever direction it happened to form. Your cutting tool slices across it. Every corner and every radius you machine cuts through that grain, the way a saw cuts across the grain of a plank. The part is the right shape, but its internal structure has no relationship to the loads it will carry. Forging does the opposite. Heat the metal until it is soft, then squeeze it into a die under enough pressure to make it flow, and the grain flows with it. It wraps around the corners. It follows the contour of the finished part. A forged aluminum fitting and a machined aluminum fitting can be identical to the eye and to the caliper, and the forged one will be substantially stronger in the direction that matters. It will also weigh less, because you can carry the same load with less material. On an aircraft, that is the whole game. The Germans had figured out how to do this at a scale nobody else had reached. A wing spar fitting that an American plant would build up from a dozen machined pieces and hundreds of rivets, a German plant would press out in one stroke. Fewer parts, fewer fasteners, less weight, less labor. In one documented case from the American program that followed, 4 forgings replaced 272 separate parts and 2,700 rivets. In another, 9 extrusions replaced 81 parts and more than 9,000 fasteners, taking 30% off the cost and 6% off the weight. So the question is, why Germany, of all countries, developed this first? And the answer goes back to 1919 and the Treaty of Versailles. The treaty stripped Germany of a great deal, including some of its most productive iron-producing territory. What it did not take was magnesium. Germany had magnesium, and magnesium is a strange metal to work with. It is the lightest structural metal there is, which makes it attractive for aircraft, but it does not behave under a hammer. Strike hot steel, and it moves. Strike hot magnesium, and it cracks. The crystal structure simply will not tolerate that kind of sudden, violent deformation. If you cannot hammer a metal, you have to press it. Slow, steady, enormous pressure applied over seconds instead of milliseconds. That is a completely different machine, and Germany was forced to build it because the alternative was not using the one strategic metal it had left. Then, aluminum arrived as the dominant aircraft material, and it turned out that everything Germany had learned pressing magnesium transferred directly. The presses that existed because of a peace treaty became the machines that built the Luftwaffe. By the end of the war, Germany had a fleet of them, a 7,000-ton press, 3 at 16,500 tons, 1 at 30,000, which was the largest closed die forging press in the world, 4 extrusion presses at 12,000 tons each, and on the drawing board, drawn up but never built, a design for a press of 55,000 tons. Then Germany lost, and the machines became property. What happened next has been described as a race, and it was not much of one. The Soviets got to the 33,000-ton press at Bitterfeld first. They took it, along with the design work for the 55,000-ton machine that had never been built. The United States took 2 of the 16,500-ton presses and shipped them home. So the post-war arithmetic looked like this. The Soviet Union held the largest forging press in the world, and the plans for something twice its size. The United States held 2 machines roughly half that capacity, in a country that had just discovered it did not know how to build them. It started quietly. In 1944, before the war ended, the government approached Wyman-Gordon in Worcester, Massachusetts, a forging company that had been making crankshafts and aircraft parts since the turn of the century. The request was straightforward. Build us something bigger. Wyman-Gordon put an 18,000-ton press from Mesta machine into a new plant at Grafton, and by 1946 it was running. It was the first heavy closed die press in America, and it was still smaller than the machine the Soviets had just taken out of Bitterfeld. The full answer came in 1950, and it came from the Air Force. The heavy press program was authorized as a national industrial project with a stated goal that was not modest. The United States would build the largest forging and extrusion presses on Earth, and it would build enough of them that no future aircraft program would ever again be limited by what American industry could physically squeeze. The original plan called for 17 presses at a projected cost of around $389 million. In 1953, that was cut back to 10. The final program cost is cited in different places as around $239 million in the money of the day, or around $279 million, which in current terms lands somewhere in the range of $2.5 to $3 billion. The structure of the deal is the part that usually gets skipped, and it explains why these machines exist at all. The presses were paid for by the government and owned by the government. They were then leased to private industry to operate, with the government taking a small percentage of the revenue they generated. Alcoa ran some. Wyman-Gordon ran others. Kaiser Aluminum, Curtiss-Wright, and Harvey Aluminum took the rest. No private company on Earth would have financed a 50,000-ton press on a commercial case in 1950. The payback period was too long and the risk was too concentrated. So the Air Force financed it and handed over the keys. The final roster came to 10 machines. 4 forging presses and 6 extrusion presses. The 4 forging presses were the headline. 2 at 35,000 tons, both built by Lowy. One went to Alcoa's plant in Cleveland, the other to Wyman-Gordon at Grafton. And then the 2 that the program was really about. 2 closed die forging presses, each rated at 50,000 tons of force, 100 million pounds. The Cleveland machine was built by Mesta Machine of West Homestead, Pennsylvania. The Grafton machine was built by Lowy. Both are still known inside the industry simply as the 50, which causes constant confusion, and both are still running today. The 6 extrusion presses went out across the country. 14,000 tons to Alcoa in Davenport, Iowa, the largest of the extruders. 12,000 tons to Curtiss-Wright in Buffalo, New York. 2 8,000-ton machines to Kaiser Aluminum at Halthorpe, Maryland. And 2 to Harvey Aluminum in Torrance, California, 1 at 8,000 tons and 1 at 12,000. That Harvey 12,000-ton extruder deserves a moment on its own because the numbers on it are absurd, even next to the forging presses. It entered service in August of 1957. It was close to 300 feet long. It weighed 8 million pounds. It could run a stroke of 92 feet, which meant it could push out a seamless missile body or a wing strut in a single continuous piece the length of a 9-story building laid on its side. And across that entire 300-foot machine, the maximum variance in the chassis was 4/1000ths of an inch. That is the tolerance of a machine tool held across the length of a city block on a structure that weighs 4,000 tons. But the machine that defines the whole program, and the one that is still doing work for the American Defense Industrial Base 70 years later, went up in Cleveland. Air Force Plant 47 sat on Harvard Avenue on Cleveland's south side, a 500,000 square foot building put up specifically to house 2 machines. Alcoa operated it, the Air Force owned it, and the thing they built inside it does not photograph well because you cannot get far enough back from it and because more than a third of it is underground. The Cleveland 50 stands 87 feet tall. 51 feet of that is above the shop floor. The other 36 feet are below it, sunk into a foundation that has to carry 100 million pounds of force without moving, which means it has to sit on rock. At Grafton, where Lowy built the sister machine, the excavation went 100 feet down to reach bedrock. That is believed to have been the deepest excavation ever made in the United States for a piece of machinery. There are elevators in that pit, running from the bottom of the foundation up to the shop floor, because a man cannot climb that every day. The press itself weighs around 8,000 tons. To put that in terms that mean something, that is enough steel to lay 42 miles of modern railroad track. But the weight is not the impressive part. The impressive part is that it had to be made, and in 1953 there was no established method for making anything like it. Take the columns. A press of this type is essentially a very large clamp. 8 steel columns run the full height of the machine, holding the crown at the top against the base at the bottom, while the rams squeeze everything between them. Those columns carry the entire load, and there is no way to build one out of pieces. It has to be one piece of steel. So Bethlehem Steel poured ingots of up to 270 tons by teaming 3 separate ladles into a single mold, because no one ladle in the country was big enough. At Grafton, a 275-ton ingot was cast to produce one single column. That ingot was then forged down, heat-treated in a furnace 112 feet long, and finished on a Mesta 96-inch lathe, one of the largest lathes in the world at the time, which removed exactly 1 inch of stock from the diameter. The finished column measured 40 inches across and 76 feet long. Then it was trepanned, which means an 8-inch core was bored out of the center along its entire length, because the center of a large forging is the least reliable part of it, and you are better off with the hole. Each column was then threaded, and onto those threads went nuts 52 inches in diameter. Not 52 millimeters, 52 inches across, weighing tons apiece. 16 major castings made up the structure of the Cleveland machine, poured in Mesta's own foundry at West Homestead. Some of the individual castings ran over 350 tons. The moving crosshead, the part that actually travels, was assembled from 8 castings totaling more than 1,100 tons. Getting these pieces from the foundries to the sites required rail cars built specifically for the job, and in some cases, parts that exceeded what a single car could carry and had to ride across multiple coupled cars. Components came from England, Scotland, France, and Japan, as well as American mills, because the American mills alone could not supply it. 8 rams, each 5 feet across, sit at the crown. Behind them, motors of 1,500 horsepower charge accumulator bottles to a working pressure of 4,500 pounds per square inch. The die table measures 26 feet by 12. The stroke is 6 feet. And here is the thing about all of it. Every calculation that went into these machines was done by hand. Finite element analysis did not exist. The engineers who designed the Cleveland 50 could not model stress distribution in a 270-ton casting because the mathematics to do it had not been developed and the computers to run it had not been built. Fracture mechanics, the discipline that tells you how a crack grows through a loaded structure over time, was not yet a field. These men sized a machine to survive 100 million pounds of repeated force using slide rules, hand calculation, and judgment. They guessed at loads no one had ever measured, in a structure no one had ever built, and they left themselves margin. The Cleveland press made its first production forging on the 5th of May, 1955. The Grafton press followed that October. They have been running ever since. Hold that fact, because it is the entire verdict on the men who did the arithmetic. What came off them changed what an American aircraft could be. The early production list out of Cleveland reads like a Cold War order of battle. Wing routes for the Republic, F-105 Thunder Chief. Wing spars for the Convair B-58 Hustler, the first supersonic bomber. Landing gear trunnions for the B-52, the airframe that is still flying and is projected to fly into the 2050s. Bulkheads for the C-130 Hercules. Later, structural forgings for the B-1B fuselage. The launch pad anchors that held the Saturn V to the tower were forged on these machines. So was the beryllium heat shield for the Mercury capsule. At Grafton, the Lowy 50 forged the main landing gear beam for the Boeing 747, a single titanium part weighing 4,000 pounds. At the time, it was the largest titanium forging ever produced. Think about what that part does. It is the structure that absorbs the moment a fully loaded jumbo jet meets a runway. Not spreads the load across a truss of bolted pieces. Absorbs it in one continuous grain flow, with no joint anywhere in the load path to start a crack. That part exists because of a press in Massachusetts that the Air Force paid for in 1953. The economics turned out to be indefensible in the best possible way. By the 1960s, the savings the heavy presses had produced in reduced manufacturing costs were estimated at $500 million, roughly double what the entire program had cost, recovered inside a decade. The savings on the B-52 program alone were estimated to be greater than the cost of the heavy press program in its entirety. The Air Force spent $250 million on 10 machines and got the money back on one bomber. None of it worked in isolation. A press of this size needs a plant around it of roughly 6 city blocks to support the full chain of operations. Ingots have to be heated and reheated, sometimes through several separate pressings, each one into a die a little closer to the finished shape, because you cannot impose all that deformation at once without tearing the metal. The dies themselves had to be cut from very hard tool steel to tolerances nobody had needed before, and some of the earliest numerical control machines in America were built to cut them, fed their instructions from punched paper tape decades before anyone said the word CNC. New aluminum and titanium alloys had to be developed to behave predictably under that kind of pressure. New inspection methods had to be invented to prove a finished part was sound, because a hidden void inside a landing gear beam is not something you find by looking. The press is the part you photograph. It is maybe a fifth of the actual capability. Both 50,000-ton presses were eventually recognized by the American Society of Mechanical Engineers as National Historic Mechanical Engineering landmarks, the Cleveland machine in September of 1981, and the Grafton machine in October of 1983. You cannot go and see either one. The work they do is defense work, and the plants do not run tours. Now, the 50 gets the attention, and it should. But it did not exist in isolation, and if you only look at the presses, you will misread what happened afterward. In the middle of the 20th century, the United States held the deepest heavy manufacturing base on the planet, and the presses were one visible peak on a very wide mountain. About 70 miles east of Cleveland's press, in Coatesville, Pennsylvania, there is a rolling mill that has been turning out steel plate since 1918. It was built at 204 inches, then widened in 1919 to 206 inches, and it remained the widest plate mill in the world for more than 40 years. It is a 4-high mill, 2 work rolls of 34 inches, backed by 2 rolls of 50 inches, and each of those rolls weighs 67,750 pounds. It ran 500,000 tons of plate a year. Steel from that mill was fabricated into the arched column supports at the base of the original World Trade Center towers. The site at Coatesville traces back to 1810 and is the longest continuously operating iron and steel site in the United States. That mill is still rolling. At Bethlehem, Pennsylvania, the ironworks built a steam hammer in 1891 that delivered a blow of 125 tons. In Connecticut, Bullard had invented the vertical boring mill back in 1883, and the descendants of that machine, some of them 36 feet across, were turning hydroelectric turbine runners, battleship turret rings, and ship propellers. There were trepanning lathes with 140 feet of bed, built to bore the center out of 60-foot naval propeller shafts, and behind all of it stood the builders. Mesta Machine at West Homestead ran what was for a generation the largest machine shop under one roof anywhere in the world, and by the 1980s, Mesta equipment was operating inside 500 steel mills. In 1981, the United States was the largest machine tool producer on Earth, with output of about $5.1 billion, roughly a fifth of the world market. That was the peak. In 1981, workers at Mesta Machine went on strike at West Homestead. During the strike, Anaconda Aluminum pulled a major hot mill contract and gave it to a competitor. That August, Mesta closed its foundry and forge shops, the operations that had poured the castings for the Cleveland 50. Net sales that year were $116 million. In the first 9 months of 1982, the company lost $18 million. On the 9th of February, 1983, after 3 banks foreclosed on a $20 million mortgage, Mesta Machine filed for Chapter 11. Most of the West Homestead works was sold that June. The last assets went in April of 1988. The company that built the largest forging press in the Western Hemisphere had been in business for 85 years, and when it went in about 18 months. Mesta was not an isolated failure. It was the leading edge. By the late 1980s, roughly 2/3 of American machine tool firms had closed. Cincinnati Milacron, which had been the largest machine tool builder in the United States since the 1920s, sold off its machine tool business in 1998 and filed for Chapter 11 in 2009. Ingersoll Milling Machine in Rockford, Illinois, which built the giant gantry machines, went bankrupt in 2003 and was bought by an Italian group. Giddings and Lewis, which had pioneered the horizontal boring mill in Wisconsin in the 19th century, passed through a series of owners and ended up under a French parent. Warner and Swasey was passed between conglomerates through the 1980s and shut in 1992. Japan, Germany, and Italy took the market. They still have it. Meanwhile, the presses themselves were being passed. This happened earlier than the popular version of the story allows, and it happened while America was still congratulating itself. The Soviet Union did not stop at what it took from Bitterfeld. At the Novokramatorsk works, Soviet engineers built 2 closed-die forging presses rated at 75,000 tons, one entering service around 1957 and the second around 1960. Each stands roughly 35 meters tall, with a die bed of 16,000 by 3,500 millimeters. One went to Verkhnaya Salda, which today is VSMPO Avisma, the largest titanium producer in the world and a supplier to both Boeing and Airbus. The other went to Samara. Read the dates again. The Cleveland 50 made its first forging in May of 1955. The first Soviet 75,000-ton press came online around 1957. America held the world record for roughly 2 years and then lost it for the next half-century. In the mid-1970s, France joined. At Issoire, in central France, a 65,000-ton press was installed between 1974 and 1976. It stands about 36 meters tall and weighs around 12,500 tons. It forges structure for Airbus and for Boeing, and for decades it was the most capable press in the Western world. It was designed and built by Novokramatorsk, a Soviet press sitting inside NATO, forging Western airliners. Then came China, and China did not narrow the gap. China stepped over it. At Dayang, in Sichuan province, China National Airchong began construction in December of 2007 on a closed die press rated at 80,000 tons. It cost roughly 1.5 billion yuan, around $200 million. It ran a successful test in 2012 and entered service in 2013. It stands 42 meters tall and weighs 22,000 tons. It is reported to take a titanium ingot half a meter thick and compress it into a thin-walled component 5 centimeters thick in a single stroke. It forges landing gear and fuselage frames for the Comac C919 airliner, military aircraft structure, gas turbine components, and nuclear pressure vessel parts. The same pattern shows up in open die work, which is where the raw ingots for the largest components get broken down. The largest open die forge in the United States is at Bethlehem, Pennsylvania, with a capacity of around 300 tons. The world-class capacity in that business is 600 tons. Japan's steelworks at Muroran holds the record for the heaviest ingot ever cast for forging at 670 tons, worked by one 3,000-ton press and two 14,000-ton presses. America is at half the ceiling, not behind on price, or on schedule, or on labor cost, physically unable to make a part above a certain size. And then, in 2008, an inspection team found cracks in the Cleveland 50. The machine had been running for 53 years. It had been designed by men without fracture mechanics, and the discipline they did not have is precisely the discipline that describes what was now happening inside it. Cracks had propagated in the structure. The foundation had cracked. The press was shut down on safety grounds. Understand what that meant in practical terms. The forging capacity that fed a substantial share of American aerospace structure went dark. And it went dark because a machine that predated the science of fatigue had finally accumulated enough cycles to find its limit. The initial repair estimate was $68 million. The final cost came in at around $100 million. The rebuild required 14 massive ductile iron castings, and among them was the largest ductile iron part ever cast, a structure of roughly 300 tons that had to be poured from 5 separate ladles of iron at 1,350 degrees Celsius, all of it flowing into the mold inside a window of 120 seconds. Miss the window, and the first iron in begins to set before the last iron arrives, and you have 300 tons of scrap and a schedule measured in years. The rebuild was engineered to a fatigue-endurable design, which is the polite technical way of saying that this time somebody ran the numbers that did not exist in 1953. The company that did the work was Simpelkamp, a German foundry. The Cleveland 50 came back online in 2012, and it supports around 1,000 jobs in the Cleveland area. It is still forging. But the machine built to close the gap with German forging technology could only be saved by German forging technology, and that is not an irony the industry particularly enjoys pointing out. Which brings us to the last press, and to the clearest possible statement of where things now stand. In October of 2018, in Paramount, California, a 60,000-ton closed-die forging press was brought online. It is the largest press built in the United States in more than 60 years. It cost $180 million, including $20 million in California tax credits. About 9,000 tons of steel went into the plant that houses it, which is more steel than was used in the Eiffel Tower. It contains 34 cast and forged components weighing between 100 and 330 tons each. It uses 270,000 liters of hydraulic oil and carries more than 3,000 sensors. Like the Cleveland machine, only about a third of its 10-story height sits above ground. The first part it forged was a main landing gear beam for the Boeing 737 MAX. The press belongs to Weber Metals, which is a subsidiary of Otto Fuchs, a German company. It was designed and built by SMS Group, a German company. The 34 large castings and forgings inside it were manufactured mainly in Europe and Asia. So the largest new forging press on American soil is a German machine, built by German engineers, for a German owner, from parts made overseas, standing in Los Angeles County, and forging structure for Boeing. In February of 2022, the Department of Defense issued an action plan identifying the areas where supply chain vulnerabilities posed the most pressing threat to national security. There were 4: kinetic capabilities, energy storage and batteries, microelectronics, and castings and forgings. 70 years after the Air Force spent $250 million to make certain that American aircraft would never again be limited by what American industry could squeeze, the Pentagon put large forgings back on the list of things the country cannot reliably make. There is a coda to this, and it is a strange one. In the 1950s, when the presses were new, the assumption was that they would keep getting bigger. Kelly Johnson, who built the U-2 and the SR-71 at Lockheed Skunk Works, and who understood better than almost anyone what large titanium structure demanded, argued that the United States needed presses of 250,000 tons. In the 1980s, the Army studied the case for presses up to 200,000 tons. None were built. The demand never materialized. Aerospace moved toward isothermal forging, where the dies are heated to the same temperature as the billet and nickel superalloy turbine discs are formed slowly in a vacuum. The largest isothermal press in the world runs at 12,500 tons, a quarter of the Cleveland machine's capacity, and it makes parts the Cleveland machine cannot. Machining moved to 5-axis and then to additive. The frontier stopped being about force. So the honest answer to whether America needed a 200,000-ton press is no. But that was never the question that mattered. The question that mattered was whether the country that built the 50 could still build the 50. And the record is now clear. The two great presses at Cleveland and Grafton are still working, 70 years on, forging structure for aircraft that had not been imagined when they were poured. They will probably outlast everyone watching this. But when one of them cracked, the casting had to come from Germany. When a new one was wanted, the design came from Germany. The machines survived. The capability to build them did not. If you want more of this, subscribe to Trade Archive. There is a lot more of this story left.